Okay. Rotary engine, which is basically the principle of the rocket. And the interesting part about Brother Beard was the fact that they said that he didn't have any formal education. So then you ask yourself, how does a person walk off the street or walk up his mother's woman and create a revolution of this type? Of course, he is an African. That was a good beginning. Then come to find out, there is a toy, in other words, trying to explain this revolution, there is a toy called Chico. Which is an advanced toy for an African child. Okay? And Chico is something of this okay? Something like that. And it's got another component like that. Okay? This is cylindrical, and this is also a little cylindrical, and it's got a piston type thing here. And what happens is you can insert a bullet-like thing over here at the, it's hollow. It's like a bamboo or something like that. They build it from. So you have this piston here, and the handle, and there's some brush at the end of the piston. Okay, so you could move it in and move it out. The brush serves as a valve. There's a valve there that when you're going in, there is a compression of air if you allow air in to begin with. And then when you come out, of course, it expands and so on. So this is a toy that an African child uses. And what happens is, with this bullet in there, you can compress enough air in here to project, send this out as a projectile, okay, or like a bullet, okay? So I looked at that, and I said, my goodness, then probably it's a relationship with that, the cheekbone, and the rotary engine, that occurring in Africa, and this man being an African. If he didn't have a formal education, the only education he had was what his father and great-grandfather taught him, which is the African education. And so there was a theory that says that is linked to cheekbone. So again, rotary engine connecting with gas turbine, and then with cheekbone. Of course, for most people who understands the good part of the other history of the African, in terms of the pyramids and so on and so forth, that is not far-fetched. That's a neat kind of thing. So this was the kind of thing that one picks up as you move on in the search for unified field theory. Every time you get something of this kind, there is a reinforcement in your efforts in terms of your determination to get the job done. So we moved on from there. By the end of this project, after having demonstrated, especially with this guy here, fine professor, Professor Wojcik, calling this work a masterpiece, that was well appreciated, and then energized me further. So then got into a field called, a field of transformation called affine transformations. While actually in high school, what I would do is, in terms of my search for the unified field theory, first I wanted to understand the relativity theory. And I remember every time I would go to the library, I will go to that section, of physics and mathematics where, you know, there will be books on physics and relativity. And each time I would pick that up, the other kids would laugh at me. Even other grown-ups would laugh at me and say, "Gee, what a crazy guy, look at the kind of crummy book he's looking at." And Michelson and Morley experiment in terms of ether and all that, I will read that over and over. And the Lorentz geometry, quite vivid. I remember the books, Dover type books, that were, and I would read that over and I would, and I'd say, gee, wouldn't it be nice if one can go beyond where they are? I'll read and just get information and move on. So eventually, the field of transformation called the affine transformation. I began to get into that. Of course, that's the same transformation that Lorentz used in explaining the special relativity. That developed, and in the process, of course, I met with a professor, in my graduate years. Actually, yeah, my graduate years. I met with a professor, a very renowned professor, called Eugene Brunel, E.J. Brunel. Eugene Brunel got all kinds of awards in MIT, became one of the youngest professors to ever be appointed at Princeton University. In fact, one of his students became the chairman of Grumman Aerospace. Renzo Caporelli was his PhD student at Princeton University. So I met him, and he was quite advanced in affine transformation studies, had developed some really neat stuff. And so I began to work with him, along with some very notable other mathematicians like George Handelman, Bob Lowy, and Henry Nagamatsu. These are some of the finest scientists and mathematicians that I was blessed to work with. So in the process, wrote some PhD thesis that did a lot of analysis of affine transformations from geometric, spiritual, aeronautical, and all kinds of dimensions. And that work received a lot of, how can I say it, praise from the mathematics and engineering communities because it has application to aeronautics. So that again energized me quite a bit. And so the fact that it had been used in relativity was always there behind, in my mind. Something that was used in relativity that is quite abstract could indeed have applications in aeronautics, designing airplanes to be safe. So I said, gee, there must be more to affine transformations, because what affine transformation did in relativity was to really explain the concept of special relativity, which in a specific form, which is the wave equation is a well-known equation in mathematics. But in terms of explaining physics, the special relativity calls for a transformation of that wave equation into a certain mathematical space. And this affine set of transformation, that the special one that Lorentz chose, could transform that equation in such a neat way that the character, the properties of the waves were preserved. Okay, there was no changes at all, and that was also one very significant. In the process, of course, he explained what special relativity was talking about, to the joy of Albert Einstein. And of course, that energized Professor Einstein to go further, into this general relativity, and beyond. And so I took note of that, but my first application, of course, was the aeronautical application in aeronautics, where obviously there are some significant problems. Most people may not realize the connection, tight one, for that matter, that exists between what you call physics and aeronautics. Aeronautics is the physics of gases and bodies that fly, through air, and so on. And so it's very much like studying physics. For one thing, air is basically composed of particles, molecules of nitrogen, oxygen mixture. And so, when you're looking at a flow, it's like looking at particle physics. And especially when it gets into the rarefied mode, then of course you're really looking at the particle. So the equations, the same equations, are used to describe those kind of aeronautical systems. So it was not totally unconnected what was happening there. It was studying physics. So, so that development received a lot of attention. In fact, in terms of research citation, the last time I count, we had, I noticed that I had over 100 citations, in terms of other researchers using, works like those affine transformation works and the current work and so on and so forth. And 100 citations is it's not a bad number at all. So then